Hmm? So, today quite a lot of things we need to do. So there's a warming up question for you. Given a m by n matrix A, how do you cook up a symmetric matrix? That is B T E equals by. Hey, wait, sorry, BT equals to B. Any idea? Impossible? Why? It's possible. Even a matrix M times N size, how to cook out a symmetric matrix. Okay. So you can consider B equals to A T A. This is a symmetric matrix. What's the size of this? N times M, which is N times N. Okay. So to be symmetric, you need to be a square first. Right? You need to be a square first. So how you make sure that off diagonal they are the same entries? So you just need to compute what is BT. Right? Okay. So using matrix multiplication, you get. So you transpose twice, you get A back. Okay. So given an M by N matrix, you just need to take A transpose times A, you get a symmetric matrix. And then from yesterday's theorem, we see that A is symmetric matrix if only if A is orthogonally diagonalizable. Okay. So that means you can diagonalize your A using orthogonal eigenvector. Okay. Is it? Yeah. Just recalling what we did. Any question? If you are still skeptical, you can just try examples. Just try any A you like. Follow this rule here. So you think, and then you transpose it and then multiply together. Okay. Good. So today plan is to do singular value decomposition and then do some revision and then point out some important part that you need to read. Yesterday we haven't done the principal access theorem. Maybe if we have time, we'll do it after singular value decomposition. But if we again, principal access theorem actually is about diagonalization. Okay. If we really skip it, maybe you need to read yourself. Is that okay? But it is really about diagonalization and then change of variables. Maybe we will touch on it a bit later. Okay, but the most important part today is the singular value decomposition. Okay. So let's start with a matrix A again. Okay, let me write singular. Okay. So what is decomposition? What is singular value? I will tell you yet. So let's aim to reach here. Okay. So suppose I have a matrix A. A matrix A. Any size of matrix M by N. Okay. A. Let's say I take A, add on some vector, call it Vi. Okay. And we compute the length. You get. So applying the formula, we have for this for the inner product. So we have AVI dot A, right? Okay. So I taking square, so I remove the square root here. Okay. So I put the square on the other side. Make sure there's a square coming at square root. Okay. So what's the definition of this? This is you transpose the first guy and then matrix multiply with the second guy, right? Still recall? Okay, good. And then what's this really? So this is just VIT times ATA VI. Okay, so from this matrix vector, how you get number out? Okay, so if we have more information, then we can get the scalar out. For example, what information? This is a matrix. This is a vector, right? So what kind of property can give you a quick number? And not that. Matrix times a vector. Split up a number with a vector, maybe. Matrix is on determinant, right? But this one is matrix on the vector. Matrix on the vector. Last chapter. Huh? I eigenvector. Okay. So if Vi is an eigenvector for this matrix, then you will have some scalar, right? So let's suppose on this stage, suppose Vi is an eigenvector for the matrix ATA. Then we can proceed further. VIT VI, which is lambda I, Vi. Okay, which is lambda I times VIT VI. Okay, so what is VIT VI? Is the inner product between Vi and Vi, which is the length. Okay. If we suppose further, okay, suppose further Vi is coming from an orthonormal set. And if we further suppose that it's coming from a orthonormal set, that means the length is 1 and then it is orthogonal to something else, then the final answer is just the eigenvalue. Okay, makes sense? Okay. So what are we going to do with this? So what are we going to do with this? So first, let's make a name here. Let's make a name of this lambda I. This wait, let me. Okay. So if we take square root on both sides, we'll see that the length of AVI is just square root lambda. Okay. So this is the important thing for us today. So let's make a definition here. How we get this lambda I. So definition. Okay. We call this square root lambda I because it's lambda I is eigenvector, but how about square root lambda I? We call it a singular value. So we say that singular values of A is the square root of the eigenvalues of A. So we will denote, usually if you see the book, you will see sigma I. I'll denote it as sigma. Okay. So maybe we name it sigma I. Alright. So whenever we say singular value of a matrix, you actually consider the eigenvalue of ATA. Alright? Makes sense? Okay. Because A here not necessarily is a square. Okay. But if you take ATA, it will become a square. A transpose A. Make sense? Okay. Please stop me if you lost somewhere, okay? Let me tell you some property. Okay, so let me tell you some property here. Some important property theorem. So what we have done just now is, suppose we have Vi up to Vn and autonomous basis. Okay. Remember just now we used this property in calculating Vi's length. Okay. Moreover, they are the consisting of eigenvalue. So they are all eigenvalue. They are all autonomous to each other. Okay. Eigenvector of ATA. Okay. Remember the two property we use here to get lambda I. Okay. Suppose we have these two property. Let's see. And suppose A has R non-zero singular value, then if you take the corresponding eigenvector from one thing to remark here is this eigenvector is not eigenvector of A, okay? It's the eigenvector for A transpose A. Okay. A might not have eigenvector because A might not be squared. Okay. So one thing to remark here is this Vi should be the eigenvector of ATA, not A. Okay. So then, but if you consider A times this eigenvector, they actually form an orthogonal basis. Orthogonal basis for a column of A. Okay. And the rank of A is R. Okay. So okay. Nothing special, just some property when we collect this ABI. Okay. Let me see. Any question up to here? Any problem up to here? No? Okay. So next. So maybe you can have a wild question. Okay. You said that if so any condition of diagonalization, or what's the condition of diagonalization? When can you diagonalize a matrix? Square matrix. So for square matrix A, when is A equals to PDP inverse. When it is when the geometric multiplicity of each eigenvalues. Yeah, sorry. So geometric multiplicity of each eigenvalue. So in the test, right, some of you add up all the power of the root. You call it an algebraic multiplicity. So usually when we talk about geometric multiplicity, algebraic multiplicity, we refer to a specific eigenvalue, not everything. Okay. So when the geometric multiplicity of each eigenvalue is equal to the algebraic multiplicity of each eigenvalue. Okay, meaning what? Meaning you can find enough eigenvectors to form the P matrix, right? Okay. But you also can ask a question: can we do something similar to non-square matrix? Something similar to any m times n matrix. Okay, can we do something like this? Yeah, can we do something like this? The answer is yes, we can do something similar. Let me bring the statement now. So if we have a m by n matrix with rank nr, okay, then we can find these three matrices here, U, sigma, and Vt. Okay, we can find these three matrices such that sigma here is also an m times n matrix, is the same size with the original matrix. Okay, and then the diagonal entry in D, there exists an m by n matrix such that the first square block, okay, with the diagonal entries as the singular values of A. Okay, not the eigen values anymore, because A doesn't have eigenvalues. Only A transpose A has eigenvalues. Okay, so we try to make use of that eigenvalues, which we call the singular value. Okay, so now we have singular value on the first square block, and then they arrange it from big to small. And what about U and VT here? Okay, so what about U and VT here? So don't know what is U and VT, but we will try and figure out what is U and VT. Thus, in this theorem, it just says that there's an orthogonal U. Okay, it is m by n because you multiply on the left side of m by n matrix. Okay, and V should be an n by n matrix because you multiply on the right side of the m by n matrix. Okay, so let me just put them together. So m by n, and then n by n, and then m by m. So you will get an m by n matrix. Okay. So let's look at this sigma. Okay, I draw the sigma out already. So the sigma says that it's an m by n matrix. Okay, it's an m by n matrix. But if let's say the r is less than n or less than m, okay, so what happened to the other entry? We just put 0. Okay, and then we put the r on the first r square block in the D. This is the piece of information you are given in the theorem. Okay? It doesn't tell you what is VT, doesn't tell you what is U, but sigma is in this form. The first R times R block has the diagonal entry singular values. Okay. All right. So far, okay. Okay. We will see example. Don't worry. Okay, we'll see examples. Should I tell you? Okay, I think I should tell you what is U and V first. Then we jump into examples. We jump into examples first. Yeah. In the meantime, you can look at it, and then if you have any question. Okay. Maybe I tell you what is U and V first. Okay. So just now, what do we have? Okay. Just now, what do we have? What do we have just now? So we have. Let me write. So just now, what do we have? So we have VI, so maybe V1 up to VR, VR or VN, maybe yeah, anyone would do. So out to VR is orthogonal, sorry, up to N maybe. Orthogonal, sorry, orthonormal is stronger. Orthonormal set, okay? And then both eigen vectors ATA, all right? And then we see from the theorem that this form a linear dependent set. Is that right? That's right. Okay. Okay. So, what's next? So you can consider UI where you normalize your vector. Okay. And we already compute that the length of AVI is just sigma I. Okay. So everything what I set up just now is not wasted because I need to use it. Okay. So the length of this AVI is sigma I. Remember, just how we compute. See, this one square is the eigenvalue of ATA. Then take the square root, become the singular value. Okay. What I say just now, don't throw away. I still want to use it. Okay. So recall what I said just now. So what we have is AVI equals to sigma I UI. Okay. So what's next? Let me see. What do I have? Jump. Hey, remember this theorem here, you see? It's orthogonal, not only linearly dependent. So it's not enough. Here is stronger. It's actually orthogonal. Okay. So you can see you got column vector, singular value, another column vector. Okay. So you got how many of them? R of them. Okay. You can do R of them together. Okay. So if we do R of them together, what do we get? Let me see. A V1 and then dot until VR equals to sigma I, sigma 1, sorry, sigma times what? Times U1 dot up to UR. that right? Yeah. Okay, so how about, but the size here is not the same, right? So if I put it, just now we say that, let me see, yeah, let me see. Okay, so let me put it here. So just now we start with m by n matrix. Okay, now here is a m by r. N, and then m by n is n by r, and then here is r by r, and then here is ui live in where? N by r. Where's ui live? Make sense? Is it? Because, yeah, okay. So yeah, okay. So since this is an orthogonal set, right? So okay, orthogonal set, but this is n by r. Okay. So how can we increase up to n? How do we increase up to n? How do we increase up to n? So we just, oh, let me use another. So we just add in all the rest in. Okay. One, two, plus. We just add all the rest in. You see, we got n of them. Okay, we just add all the rest in. But what happened to the rest? Actually, they are correspond to the singular value, which is 0. Okay, so sigma r, and then 0, and then keep going up until 0. Okay, so actually they are 0. So how about you? How about you? How about here? How about here? How you add until m? What vector you can add? What vector you can add up to n? M. You just add 0. Yeah, you just add 0. So you just add enough 0 to get uh, column. Because when a multiply on vr plus 1 to vn, you get 0. Okay. So the obvious vector to add is the 0 vectors. Okay, so this means that a can be written as u1 dot 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 ur or dot 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 or. Okay, be careful here. When I say this u1, right? So don't throw away my construction. Please remember this construction. So when you do the example, right, you must use this construction. Later we will see again, but I want to teach you how to read this. So then we can multiply by the sigma matrix that we call in the theorem, and then 0 and replace. And then because this is orthogonal, right? Orthogonal what property? The inverse is the, how to find the inverse of an orthogonal matrix. Orthogonal matrix satisfy what equation? A equals to identity. So what's the inverse of orthogonal matrix? A transpose. Okay. So you just take the transpose. So you just take the transpose of V. Okay. So this is how we make up the U, sigma, and VT. Right. Okay. So you can see that quite random. I didn't do any example, but using the probability, we can find this. Okay. So let's dive into example now. Okay. Let's do example. Okay. So the example is very short. Not very short. I mean, the question is very short, but the example, the calculation is long. So examples. Okay. Example is construct singular value decomposition of a matrix 4, 8, 1, 1, 7, 14, -2. Okay, so so you need VI, you need singular value. Yeah, singular value. You need VI. Okay, so which one you do first? You need VI, which is an eigenvector. You also need singular value, which is an eigenvector for ATA. Okay, so which one to do first? Any idea? Step. Okay, first step, we can find the eigen values of ATA first. Okay, so let's find the eigenvalues of ATA. So, so what's ATA here? Have we done this calculation before? Yesterday, did we do it? Or no? Did we do it? Or the first thing we did in the morning? Let's see. We done this calculation? Okay, maybe we compute what is ATA first. So what is ATA? Okay, so you transpose, and then multiply ATA. So A equal 7 times 2. Okay, what's this? 16. Seems like, let me see. Can you do this computation? What is ATA here? Does several got this? Yep. Got it? Got it? Okay, some of you got it. Okay, so from here, what's the characteristic polynomial? Calculation is a pain. Cheat a bit. So I cheat a bit, I tell you what is it. So this is a lambda minus 360 lambda minus 90 times lambda. Okay. But if outside lecture time, you should calculate. Okay. Yeah. So you just do the normal job. Yeah, it's a pain, I know. So you just take your ATA and then minus lambda. ATA minus lambda. Okay. Sometimes if a question is easy, you can use some the trick you use to compute the determinant. Sometimes you just have to do cofactor expansion. That's the only way. Okay, so let's us chill a bit. So we got this already, but later I'll let you do another exercise. So then we'll do that together maybe. Okay, so we got 3 lambda here. Okay, we got 3 lambda here. So how to get singular value term? Singular values. Singular values. Okay. What's the singular values of A in this case? Remember what's the singular values is? We compute the the length of AVI square equals to lambda I. So to get the length, we need to take square root. Okay, so we take square root of lambda I. So let me put here lambda equals 360, 90. So singular value theorem, singular values are square root 360, 90, and square root 90, and then square root 0 is 0. All right, make sense? Okay, so far okay. Yeah, so which is equal to 6 times square root 10, 3 times square root 10, 0. Okay, so um this is the singular values, but we also need VI, right? Remember what is VI? What is VI? Is the eigenvector for ATA. Okay, is the eigenvector for ATA. So it's the eigenvector of ATA. So you need to put everything you have learned before now. Okay. So find V, which columns are eigenvectors of ATA. Okay, these are eigenvectors for ATA. So eigenvectors of ATA, how to find? So you need to find lambda equals to 360, lambda equals to 90, lambda equals to 0, and then compute the lambda 360i, lambda minus 90i, a minus 0i, okay, and then row reduce. I realize that some of you cannot read the null space of this matrix. Maybe you miss that eigenspace is a null space. So every time I do this, I never do the augmented matrix version, right? You notice in my note because I skipped that. I think next time I shouldn't skip because if you lost there, then you don't know how I get the null space solution. Okay, but now you should pick up that after I do this, you should augment with the 0 vector. Okay. Okay. Yeah, I realized another thing. Is you don't listen to what I say. You only pay more attention to what I wrote. So something I said very important, right? But it's very trivial. But it's important, but it's trivial. It's subtle. So then you kind of miss that part, but I didn't write it down, but that's important. So sometimes what I say is more important than what I wrote. Of course, writing down will be easy for you to check, but what I say is also important. Okay. Yeah. Listen every word that I say. And then If I say something wrong, you ask me. Okay. Yeah. Not just what I wrote down, but also what I said. Okay. Yeah, okay. Okay. Um. Yeah. What? Okay. So this is also a pain. So let me skip this. Later we will do one exercise together. We spend maybe longer time to do one exercise. Okay. Now I lay out the step first. Okay. Let's skip the trivial calculation. Okay. So let's say we say that we get eigenvector for the first one, 1 over 3, 2 over 3, and 2 over 3. Don't worry, we will spend maybe 15 minutes to do one example together. But now I want to lay out the step first, the plan to find. Okay. Okay, so here I should put lambda equals to 360, and then lambda equals 90, and then v lambda equals 0 is what? 2 over 3 minus 2 over 3 minus 3. Okay? Okay, so you might ask, hey, why these v are orthogonal? Just now we want v to be orthogonal, right? Because we want to take the inverse as the transverse. So why is this orthogonal? Why these eigenvectors are orthogonal? Yeah. Why they are orthogonal? Okay, can you see that they are orthogonal now? So why are they automatically orthogonal? Remember the first thing we do in the class. ATA is symmetry. This is the eigenvector for ATA. Symmetric function is orthogonally diagonalizable. How you diagonalize? You find the eigenvector. So the eigenvectors are okay. So everything I do, right, don't take it trivial. What I say is what I need to use later. And everything I did from the quiz to the back, everything I need, I will say first. Okay. So keep remembering what I say. Okay. Okay. So done. We found VI. We found sigma. The next step is to find U. Okay. So what is U? Find U. Remember the construction just now. Okay. Our U is UI equals to 1 over the sigma I times AVI. Okay, times AVI. Right? Okay, so this is our UI. So what do we need to do? So what do we need to do in this case? So we got how many VI here? We got actually 3 VI. Let me see. Let me see. Our A is what size? Let me write down. Our A is what? 4, 8, 1, 1, 17. Sorry. 7, 14 minus 2. Okay. Our A is a 2 by 3 size. Okay. So U have to be what? Let me see. Let me write down. A equals to U sigma VT. So our A is 2 by 3. So U should be 2 by 2. And then sigma should be the same size as A by 2 by 3. And then V should be 3 by 3. Okay. So just now we found a 3 by 3 matrix already. And then we have sigma. Sigma, we got 3 singular value. Okay. But we just only care about the non-singular one. Okay. So let us put our sigma as what? Let me write down the sigma. So the first one we get is 6 times square root 10. And then the second one we get is 3 times square root 10. Right? Yeah. Okay. So we only care about only care about 0, non-zero singular value on the R times R. Okay. There's extra 0, right? So we don't put this extra 0 here. So there's no 0. Okay, we don't want 0. Okay, we just care about the non-zero one. Yeah. Okay. So we also got V already. Let me put it here. Wait, let me put it here. Put it here. Put it here. So we got a 0 for the VT, which is this 3 guy here. Or maybe I put it here. So V is actually equals to these 3 vectors here. Okay. So we need a VT here. So to get VT. Okay, after we get VT, we need to find U. So U is just A times VI divided by the singular value. Okay. Notice that A times VI is not lambda VI, okay? Because what? Because VI is the eigenvector for ATA, not A. Okay. So AVI is something else. I don't know why is it something else. So you need to take AVI, divide by sigma I. So do I have AVI on my hand? Okay, I did. So we need to, for example, compute this. Okay, after calculation, A1, sorry, maybe I should write a bit longer so that you know what's going on. Sigma 1 AVI. Okay, if you do this calculation here, you should get this vector, and then this is your U1. Okay, and then similarly, you can get your U2. And then I just try out the final answer. And then if you arrange this as your U, so U equals to 1 over, okay, after simplifying, you will get this number. I would say this number is not very important, but you need to know how I put this number together. Okay. This number is just some calculation. So in the exam, right, if you are really careless, right, but you got all your step down, so you will just get deduct mark on the calculation, maybe 1 or 2 marks. Okay. But the step is really important. So every step, how you do, how you find, very important. If you have some careless mistake, maybe 1 or 2 marks deducted. Okay. So this step is very important. So the claim is if you put this U, okay, put the U, put the sigma, put the VT together and multiply together is your A. Okay. It's not a square by not a square matrix. Okay. Any question on this process here? First, okay. Do you have any questions on this process? On how to find sigma, how to find V, how to find U? Any question? This 3-step here. Any question? So one key point here is we only care about the non-zero singular value. Okay, we only care about non-singular. If not, maybe we have a break until 10 o'clock and then we'll come back to one exercise again. Okay. 东西。这种很太快，这样希望考试会好。还有侧重吗？这个。等一下我那加工的。哎，跟那个这个这个特征知道那个，两个这个，不，那个哦，那个我们没有做过，都是我新来去看认识。看一下，看一下会难症吗？啊，我看一下会难症吗？好像应该不会太难症诶，但是我说我没有在班上说过了。难不难症啊？给我想一下哈、想不出来。哦，很难症，连那个书都没有，那个很难症啊。就是 symmetry 的话就，啊，这两个是，然后这个这两个怎么可以跨过去？然后为什么可以呢？为什么它可以跨过去的？往这边不转，这边可以内部转，知道？为什么可以内部转？说你说这一列等于这一列的地方，对啊，你怎么可以内部转呢？它这个东西取出来的是一个 inner product，而且哦，你怎么保证？哦，因为它是 square，像这样子，这个真的是，这个是一个 vector 来的，不是一个哦，project，没有，你要对，你要。 2个 eigenvector 动起来就可以出来。Oh, okay. Let's together go through this example. Okay. Let's together compute this example. Go through all the nitty-gritty details. Let's go through the detail where we want to find the singular value. Okay. Let's start try and compute eigenvalues of a singular, sorry, ATA and singular of a. Okay. Let's together go through these nitty-gritty details. Huh? Oh, okay, what's going on? Okay, yeah. So let us go through together all the details. I would say this kind of question definitely is in the exam. That's why I spend time doing it. Yeah, let's do together. Although I assign you a lot of tutorial question, right? Actually, I do the tutorial question like you. Yeah. So I know how much time about. Maybe you should spend more than me or less than me, depends. But at least I know how much time you guys spend. Sometimes doing tutorial question is longer than preparing the lecture. Everyone, please do this exercise. Do this exercise. Don't sleep. Do this exercise. This will help you pass the course. Actually, this class the hurdle is not high. Yeah, there's no like last time I have a triple pass course where you need to pass midterm, need to pass final, need to pass the whole. But this course don't have. It's just like total pass. Yeah. So final should save you. Like final have 60%. Although your quiz result is not too bad, right? I don't think someone will fail uh, based on the quiz result. But if you want to get good result, you definitely should work a little bit harder. Okay. And just find me if you have any problem or question. I like this kind of symmetric question where you can compute the solution easily. That's why I like the symmetry a lot. That's why I'm in the algebra side. If you're in the calculus side, you go and estimate the little small thing, and then look at different versions. Yeah, it's a bit. Huh? Oh yeah. Sorry, sorry. Today I'm a bit off. Just today, this morning, I forget where I park my car. And then when I come to the car park, and then I stop at the A5, and then I think today should be in A. Today I'm a bit off. Mm. The result of sleeping late. Everyone got or not? Eigenvalue. Can find eigenvalue? Yeah, sometimes, yeah, I skip the part equal to 0, even for determinant, even for null space, because we assume you know already null space very well. So we talk about definition and then straight away use the null space. You know, like you augment a zero vector versus you don't augment a zero vector doesn't affect how you read the solution. Okay? Because you still read the solution from the A. Anyway, I will go through this thing again later. Hopefully you will understand. If not, you should come and see me. Because sometimes it's just the channel not right. It's not that good. Okay. Often is the channel not right. If you tune to the right channel, then you'll see it. Does everyone got this? 18 and 0? Got it? So the singular values are then sigma sigma y is 9, and then sigma, do we need sigma 2? Just write it for first. Sigma 2 is 0. Okay. Okay, so what's the next step? Everyone got this? Got this? Please hands up if you don't get this. Okay. So if we all got this, then we continue. If you still left behind, you can catch up, and then if you can't, then you ask me, stop me, go back, goes down. Second is to find what? V or VT, which columns, okay, maybe V first, which columns are eigen vector of ATA. Okay, so I'll go and find. It's okay, can see? Can understand this? So find eigenvector of ATA. Okay, another thing I want to teach you, another technique. Okay, when I say find V, right? Okay, what is V? Don't go anywhere and find V. I already said it here. Which columns are eigenvector of ATA? Okay, so the part behind that describe V is more important than V. V is just a name. Okay, what is important is what is V. So the important part is here. Okay, okay, can you see? What happened? Oh, yeah. Sorry. So get three sigma. Okay. Okay. Eh, okay. So okay. So okay, find V. Okay, let's find V. What's the eigenvectors of ATA? Try this matrix. Thousand. How many days? 6 days. 6 days. Yeah. Don't give up. After 6 days, you can done. Right about it. Okay. Yeah. I want to see everyone do. Or you get confused with a mixing of equal and raw equivalents. Because we assume you know uh, the previous topic. So I combine all the things together. Okay. If you're not sure, then you write step by step. So whenever you see something not right, you should definitely point out and let you know. Have everyone got the eigenvector yet? Eigenvector. Is this the eigenvector you want? Are they orthogonal? They are orthogonal, but they are not orthonormal yet. Okay. We want orthogonal matrix for V. Okay. So really, I haven't point out the key point here. So we want to find orthogonal V. Orthogonal. Okay. So that means we cannot stop here. We need to normalize it. Okay. So take the normalization. Divide by the length. Okay. Need to take the normalized one. Okay. Because we want orthogonal matrix. So orthogonal matrix come with two, orthogonal and orthonormal. Okay. So not just eigenvector only, but the orthonormal one. Okay. Everyone follow? Okay. Fine. Alright. The back follow or not? So you need to take orthonormal vectors. Okay. So V have to be orthogonal and orthonormal, which we call orthogonal matrix. Okay. So let's continue. Find U. Okay. Find U. Find U. So what's the formula of U? The columns are ui equals to 1 over sigma I times AVI. Okay. So let's see what's the size of U. So A is what size in this case? A is a 3/2 size. So we have a U, sigma, and VT. So VT should be a 2/2 size. Sigma is the same size as A. U is the
3 by 3 size. So you got U1 equals to 1 over sigma 1 AV1, U2 equals to sigma 1 AV2. How about U3? U3. But you can start computing what is U1, U2 first. Then later I'll tell you what's U3. The theorem, I think would be something else. U should be orthogonal as well. Okay, so you have to be orthogonal. So we cannot just add 0. So we have to add something special to make it 0. So what is U3? U3 need to get it from the Graph. How to do Graph? You compute U1 and U2 first, then later I'll tell you how to get U3. Anyone got U1 yet? U1 is it something like 3 times square root 2 times 1 over 3 over 3? This one? Has anyone got this? Got this? If not, you check your calculation again. So this is 1 over 3 times square root 2. A is what? 1 minus 1 minus 2, 2, 2 minus 2. One is the thing we found is sorry, equal to the left-hand side. Yeah, try and compute this, right? Yeah. Okay. How about the U2? Ah, cannot see? What? What's wrong? What's wrong? Let's see. What's the sigma 1? Sigma 1 correct. A correct. V1 correct, right? What's wrong? Hmm? Which one is wrong? Huh? What are you trying to say? What's wrong? Oh, you mean this one extra? Okay, okay. This extra scalar, is it? Yeah. So what's AV2? AV2 is 0, right? Is it 0? You guys get 0? You get 0 on this one? Get 0. So how to make U2 and U3 now? Right. How to make U2 and U3? How to make U2 and U3? Okay. So first we know that we want an orthogonal U. Right? We want an orthogonal U. Okay. So we need U2 and U3 are orthogonal to U1. Okay. So how to find two vectors that are orthogonal to U1? This also this. Okay. Maybe we set x1, x2, x3 because we don't know how to find, right? We set this condition here. Okay. So we set these two conditions here. And then what do we found? We found x1 minus 2x2 minus 2x3 equals 0. Right? Okay. So you need to find x1, x2, x3, which is equal to 0. Make sense? Okay. So just now what we do here, there's something wrong with this one, this slide here. So we cannot just use 0 because we want orthogonal actually. So where's this? So we need to, so this part here, so let me put it here again. So this part here need to be orthogonal. Yeah. So orthogonal matrix. Okay. If orthogonal, that's okay, but need to be orthogonal matrix. So the length has to be 1. So we cannot put 0 here. We need to extend. Okay. So to extend, we need to find vector that satisfy this condition here. Okay. Find the condition here. So you see, now we put everything we learned together already. So how to find x1, x2, x3 such as this whole? Okay. How many free variable? How many free variable? Free variables. 1 minus 2, 2, 0. Okay. How many free variable? Huh? 2. Okay. So what's the 2 vector here? Spanned by what vector? The null space here. E. Okay. Let me write it down here. So x equals to x1, x2, x3, okay, equals to what? Plus x2, minus 2x3, x2, x3 is 3. X3 is 3. And then I circle the pivot. So this is the pivot. Can I read this? Parameter. Okay, parameter matrix 1. Okay, so we can write it as a span of 2 vector here. 2, 1, 0 plus x3 of minus 2, 0, 1. Okay. Okay. So meaning what? Meaning what? Meaning these two vectors are in the null space of this equation here, the matrix here. Okay, is it okay? So far okay or not? So far okay. Lost already? Lost already? So far okay or not? Okay. It's okay. First week only. First week. Let's go back to first week. Okay. So now we have what? What we have? So what do we have? So we have this vector, where this vector is orthogonal to this vector here. Okay. So they are orthogonal, right? Is it orthonormal yet? Not orthonormal yet. So they are both orthogonal to this guy, right? Okay. So let me call them first. W1 is 2, 0, 1, and W2 is minus 2, 0, 1. Okay. So we can see that W1 is orthogonal to 1 minus. Does it have a name? U1, okay. U1, so U1 is 0. W2 talk with U2 is 0. Okay. So the next question is it W1 and W2 are W1 W2 orthogonal to each other? No. Okay. So what to do? You got 3 basis vector. You want to make orthogonal basis. What do you do? What's the process? What's the process? Grant Smith. Okay. So Grant Smith, very good. So if you don't know Grant Smith, you cannot leave this course. So you got U1, okay, is orthogonal to W1 already. But W2 is not orthogonal to W1. So you need to produce U3 using the previous two orthogonal vectors. We are trying to put everything we learned together. Okay. So let me write down. Since W2 dot W1 is not 0, that is, they are not orthogonal, we perform Grant-Smith. Okay, Grant-Smith to W2. Okay, to W2. Okay. Yeah. So do you know how to do Grant-Smith? Okay. There's 2 choices here. There are 2 choices here. You can project on W1 is enough, or you can project on the span of W1 and U1. Yeah. You get what I mean? So if you project on W1, right, you take the difference
then the vector is orthogonal to W1. Okay. And then if you project on project on W1 and what's this? U1, then if you take the inverse and take the difference is orthogonal to both of them. Okay. But this one, since W1 is already orthogonal to U1, so the one you create will also be orthogonal to U1. Okay. Okay. To be safe, you just do this. Just do this. Okay, just do this. Okay, let's do this. So let's perform Grant-Smith to W2. In the textbook, they just perform Grant-Smith to W1. Okay, you can try and compare. Okay, they just do it on W1. We can do it on both. So okay. Yeah, just more work. They perform on W1 less work because there's only one thing you need to take away. Okay, so let U3 be equals to R. You get W2, right? So what I mean, right? W2, W2. Okay, W2, take away the projection of a span on W, which is on W2. Okay, then you compute what is W2. So minus 201, take away the span is minus 201, dot with W1, 210, over the length of 210 times 210, take away the minus 210 dot with U1. What is U1? This one. Yeah, this kind of question can be long. So you have to do a few of them to make yourself get used to this kind of calculation. Because there's a lot of calculation going on, so maybe easy to make mistake. But as I say, the end calculation is not as important as the step. Okay? We allocate a lot of mark on the step. Okay? If you really find you have no time to do it, then you just lay out the main step. So the final answer will maybe deduct 2, 3 marks, something like that. Yeah. But the main step got a lot. Throw away those marks. So just try hard. Try anything you can. I mean, that's the last resort. Okay, what's this? Yesterday, I spent about 1 hour to check one of the exercise in your lecture, in the lecture. I provide the two-way to compute the least square solution. Have anyone of you see the latest one? Let us know. You should go and see. Because I also did some calculation wrong and I keep checking. Actually, I did both calculation wrong. So I need to cross-check and then check this one, check that one, check this one, check that one. And then in the end, finally work out. So I tell you, it will work out, but it takes time. Yeah, it takes time. It will work out, but it takes time. Hey, in the meanwhile, anyone calculating this U3 here? What's this U3? Anyone just shout something out.
Maybe it seems like you guys cannot see it. Like too thin. Anyone done calculation? I believe the calculation from accountant. I checked that the quiz, right? All the account count very accurate. I mean SEC for SEC. Yeah, very good. Accountant have to count. Can got this? Anyone got this? What is U3? What is U3? What is U3? Anyone got this? Jinghao, you got it? Is it Jinghao? Ah, Jingchao, yeah, Jingchao. Have you compute? What is this? 45. Okay. Okay, it's 45. And then 4 over 45. And then it turns out to be the same as you if you just project on. If you just project on. Let me see. Okay, never mind. I'm going to say this. Okay. So so what's next? So you got your U1. Got this U1 is, and then you got this W1. Where's W1? And then you got this U3 copy. Okay, so you got these three. So you want orthogonal matrix. So you take U equals to U1 divided by the length, W1 divided by the length, U3 divided by the length. Okay, to get orthogonal matrix. Okay, it's okay. Okay, so you got U, and then how about have we got sigma yet? So let's put the size, and then to check what do we want. Let me this here. So we got this U. And do I need to go through this computing the length? Because I realized that you cannot do normalization in the quiz. So what's the length of W1? The length of W1 is square root 5. Right? Okay. So you need to take W1 divided by the square root 5. Okay. And then also compute what's the length of U3. I believe. Yeah, I don't believe. Never mind. So compute U1, the length of U1, the length of U3, and then you take division. Or maybe can someone quickly compute what is U1, just in case? What is U1? The length of U1. 224, 224, 224, 4, 8, 9, 3 by 3, 9. So this one is 1. Okay. What is U3? 4, 4, 16, 16, 25, 1, 51, 51, 55 over 55, 1. One, huh? Okay, good. So U is just to be complete. So I put this vector down. Paste. And then this one. Paste. And then this one. Okay, this one shouldn't make this big. This divide by square root 5. 2 over square root 5. 1 over square root 5. And then 0. Okay, so this is our U. How about our V? So let me put here, cut, then paste. We found our V, right? So where's V? Bring it down here. Let's bring the V down. Copy. Okay, these two. So let's copy. Paste. Again, we got this V2, V1, and V2. So we put them side by side. Big. Okay, like this. I'll put square root 2. Okay, so this is our V. Okay, how about sigma? Sigma is a 3 by 2. So we need to put our sigma 1, sigma 2. Okay, this is a 3 by 2. So you complete it by a zero matrix, which is 3 sigma 2. Is it 3 sigma 2? 3 sigma 2, right? 0, 0, 0, 0. So maybe I make a color on the singular value, just in case you don't confuse where the 2 comes from. Okay, so now done, I think. Hey, is this the right size? 3 by 2, oh, sorry. Sorry. Okay, 3 by 2 look like this. This now is a 2 by 3. Okay, I think should be done now. Let's check, is it correct or not? Let me see, the V. Yeah. Okay, V. So if you want to make it VT, then you need to transpose this V. Okay, just transpose it. Transpose. Can do transpose. Just transpose. Transpose is the same in this case. So equals VT. Okay. So this is the wow, we spent about 1 hour. So make sure you try more example. Try more example. Okay. Just follow this one and then try more example. Yeah, mathematics is like that one. You think you know, but if you don't try enough, then you still cannot work out. So you need to just keep trying. So because the time is short, right? So I'll give some hint for this chapter 7 is you do more example of this. Just do more example. Okay. For the principle, I want to say something on this principle as this. I don't know if it's in the exam or not, but I want to say something on this. So if you go and check this, right? So yesterday we learned the quadratic form. Okay. Is it? Okay, different way. Sorry. Okay. So let's say A is diagonalizable. Okay. If A is diagonalizable, then we can write something like this. Which way? A equals to P D P T. So T equals to P T P. Okay. Okay. So then we can write what? We can write yeah. So we can write like this, and like this. Okay. So this is a diagonal matrix. Okay. And then this part is called the change of variable. Okay. So this P here, right? You remember last time we always say change of basis, change of basis, change of basis. So if you apply the change of basis element to the variable, you change the coordinate. Okay? It's still coordinate, but you change the coordinate. You can look at the textbook, for example, but I tell you what is going on there. So after you change the variables, right, and then you will change the effect of A. But this A is just a diagonal matrix now. Okay. Right. So diagonal matrix has a property. Remember yesterday the example we shown. For example, if we have X P on 2, 1, 0, 0 and X, right? So for example, this is X1, X2, sorry, X1, X2, 2, 0, 0, 1, and then X1, X2. Okay, what do you get? You just get 2x1 squared plus plus what? Plus x2 squared. Okay, if you do the computation. So it means that there's no this weird term coming out here, the cross term coming out. So you can remove the cross term. Okay, if your A is a diagonal, there's no cross term. But if your A can be diagonalizable, you can change your variable such that you get this kind of form. Okay, this is the principal access theorem. You can go and read. I think it's not hard to read. The key point is here is you can do diagonalization, then change your variable such that your quadratic form is just sum of xi squared. Okay, yeah, that's all. That one nothing special. If you want to look at the geometric interpretation of these things, is you can think of it as you rotate the graph, rotate the ellipse. If you see the examples in the book, okay, it's just rotating. Change of variable is rotating the graph. If you want to talk about geometry, okay, maybe let's don't rest. Okay, let's not rest. Then we just do some overview. Okay, last night I wrote down about 7 page, almost write an essay already. Okay, let's talk about overview. Let's look at this linear algebra overview, and then I will point out some key part that you need to definitely learn for your exam. Okay, so that you don't spend some not necessary time for different stuff. Okay, let me prepare my folder. In this summary, I will say some keyword that you necessarily need to know. Okay, so overview. Well, we've come through this 5 weeks journey, finally come to the end. Okay, so first topic 1. So we have the system of linear equation. Okay, so we start by looking linear equation. Linear equation cut through hypersurface in Rn and cut through a subspace. And then you want to solve few of them together, you are looking at the intersection. So either they intersect, either they don't intersect. So you lead to some inconsistent system or some consistent system. Okay. So inconsistent system, you don't have solution, but consistent system, you have either one or more solution, right? Yeah, if you don't understand what the word I say, maybe you can point out, and maybe I can give some more as example. So how to solve it? So we use the elementary operation row. What am I saying? Elementary row operations. Okay. Every elementary row operation contains what? Replacement, interchange, and scaling. Okay, these 3 scaling. Okay. And then how do we solve it? How do we solve it? So we solve it by looking at the reduced row echelon form. Reduced row echelon form. Don't just copy. Please listen to what I say. Make sure what I say is correct first. So reduced row echelon form is unique because I will give you in the end this thing. So it's unique for each matrix. Okay. Make sure everything I say makes sense first, and then you only accept. Then second, you will look at how many pivot position, how to solve it. Okay. And then compare with the free variable. Okay. So also you will see free variable from the homogeneous system if you want to have a non-trivial solution, right? Non-trivial solution. So this one go to here by non-trivial solution to homogeneous system. Okay. And then there's a weird theorem come out in the middle, the four equivalent statement about the spanning set, right? Four equivalent spanning statement, right? Theorem. So one of the gist of this thing is every row has a pivot. Yeah. Every row have a pivot, then you span. So the main thing to take away from this three part is you go from linear system to vector equation to matrix equation augmented matrix where you really do hands-on, where you get your hand dirty. Okay. And then after talking about span, whether got solution or not, got span or not, then after we go to linear independent. Okay. After linear independence, we look at linear transformation. Okay, now here I want to put a star on linear transformation. So this linear transformation is still between Rn to Rm. Rn to Rm. I talk relatively fast, so just make sure what I'm saying is makes sense first before you accept it. So have two property here, on two and one to one. Okay, so I want to put a star here is, for example, you need to know these things. So for example, rotation can be written as a half rotation can be written as a matrix form. I'm not saying that rotation will be come out in the exam, but this kind of question will come out. Okay. So I tell you how vectors change, but I don't give you the matrix, how you produce the matrix. So you need to check on the standard basis. Okay. So let me put it here. Let me give you the way. So the phi matrix A for T, let T add on standard basis. Then A equals to T on E1. Make sure you review this thing. We're already gone through in the class. So TEI will make up the columns. TEI will make up the columns. Okay. Oh, let me see. Yeah, that's all for chapter 1. Okay, next. Next part we do matrix algebra. So matrix algebra started relatively easy. We do addition, we do scalar multiplication, matrix multiplication also. Okay, because this is an algebra, so it got extra operation here, multiplication. Okay, and then we found that we found elementary matrix. Okay, so now we go up a level. Just now you only know how to do row operation, but actually row operation is a matrix multiplication. Okay, so we go up another level. So elementary matrix to realize elementary row operator. Okay. And then we learn how to find inverse, 2 by 2 inverse formula. Okay. Invertibility. Okay, invertibility. And then we learn subspace. We learn subspace of matrix. How to learn subspace of matrix? We look at the null space of A. Okay. Also up another level. Just now we study the homogeneous system, right? So now we turn to talk about null space of A. That's why every time in the eigenspace, I keep dropping the augmented matrix. Because when I say null space of A, then it's solving the homogeneous system. Okay. So this is where I make the quick change in chapter 5. So we have null space, we have column space. Okay. When we ask whether there's a solution to this system of linear equation or not, and it's going to be, it's asking the same question as, is B in the column space of A? Okay, we up another level already. We're talking about space. We don't want to solve different equation anymore. We talk about space. Is it living in this space? Okay, if it's living in this space, then we can solve it. If not in this space, we cannot solve it. That's why in the chapter 6, if it's not in the space, we project it down into the space and then solve it. Remember this square, we project it down and then we find the S hat. Okay. So make sure it is in the column space of A, then the system is consistent. And we'll continue, then we will talk about the chapter 6 again later. So we have column space, null space, row space of A. So vertical, we see horizontal, we also see, okay. And then from here, we can get basis, right? Pivot, number of pivot, so, sorry. So basis, okay, I don't want to point out. Yeah, okay, basis, and then we can count the dimension. Remember, we count how many bases. Depend on what dimension, you call it rank. Dimension of core A, we call it a rank. And then we got a rank theorem. So we combine, we relate dimension of different space. Dimension of null A is plus dimension plus, sorry, let me write down. So dimension of null A plus rank A is equal to whole the n the if A is a m by n matrix. Okay. And then we got the basis theorem. How to find the basis? Okay. Linearly independent and span. Right. Measure linearly independent and span. We can add linearly independent bases and then, or we reduce the spanning set to get linearly independent vectors. Okay. And then we also learn the one last thing is the coordinate vector here. Okay. Because once we got the basis means every element, you got infinitely many elements, but you only need these basic vectors to describe that vector. And then it is uniquely. Okay. So that's why we got this coordinate vector here. If it is not unique, this coordinate vector wouldn't work. Okay. It's not useful. It is unique. We want to take the coordinate vector. Okay. Okay. This so far this one okay. Okay. What's next? Just no topic 3, right? Okay. So straight away we jump into another level, level 3. Level 3 is vector space. Okay. We leave the world of Rn. Okay. So vector space, we leave the world of Rn. Because the slogan here is our world is modeled on vector space. We try to imitate this world as vector space. Okay. So this is the slogan. So similarly, we learn the definition of vector space. Okay. So definition of vector space. We also learn subspace also. It's kind of repeat of what we do for Rn because this is just a generalization of Rn. So subspace. Okay, this one I want to put another star again. We have a what? Quiz on this. So make sure you know it. You know how to do again next time. How to check uh the closure, the subset property, the closure. Sorry, zero vector first. Zero vector. Also, is the presence of zero vector. If you don't understand what I say, right, you just listen first, okay, and then go back and you make sense of it. And then closure of addition, of scalar multiplication. Okay. So make sure you know how to show. And then one easy way to get subspace is to just take the span of vector. Okay, this is an easy, cheap way to get a span. Yeah, just take some vector and then take the correct, consider the span. And then we also touch basis again. So it's linearly independent and span. And then we provide some theorem on how to find them, how to test whether something is a basis or not. One of them is the spanning set theorem. And then the other is the linearly, I call it a linearly independent theorem, but that theorem has no name, but something regarding linearly independency. And then these two together form the main basis theorem. Okay, so from here once we got a basis, we count dimension again. Okay, just count the number of vectors in the dimension. And then from here, again the same. We have the coordinate vector, which we call the unit representation theorem. So we have coordinate vector. So this we have made isomorphism between V with basis, finite dimensional V. Okay, we made a relation between finite dimensional V with Rn. So finite n dimensional V with Rn, so n basis. And then we got this basis, right? So maybe sometimes, okay, sometimes you guys will ask a question, maybe very rebellious. For example, x1, for example, let me put here, x1 plus x2 plus x3 equals 0. I also asked this question before. If you want to express s1 equals to minus 2 minus s3, why not we express s2 equals to minus x1 minus x3? Why not do this? Isn't it they are the same? I want to say that yes, you can. That's why we come up with this change of basis. Okay, so to relate these two is just change of basis. Okay, the pivot position is an easy fast way for you to see. But if you want to move your pivot anywhere, as long as you keep track of it, it's fine. Okay, so change of basis. So change of basis here. Okay, let me remark here, change of basis. So let me read up chain of basis. So what do you learn in chain of basis? You put two bases side by side, and then if you reduce one of them to identity, you get the change of basis vector. Okay. Another thing you need to know is what does this change of basis matrix doing? So this change of basis matrix doing is if you put a coordinate relative to B, you multiply by the matrix, you will get coordinate vector relative to C. This is by definition. And then if you want to change the other way, you just take the inverse. How to find the inverse? There are various ways to find the inverse. Oh, chapter 3. Chapter 3 is about determinant, right? Where's my paper? Jay. Where's my paper? I remember I wrote this yesterday. Okay, later we'll go back to chapter 3. Because when I talk about minus inverse, right,
there should be a chapter telling you how to compute the inverse, which is the Cramer's rule stuff. Where's my paper? Oh, it's at the bottom. Okay. Okay. Yeah, chapter 3 is quite short. Okay. So chain of bases, we should stop here first. And then we really, okay, let's go back to chapter 3 and then we go to chapter 5. There's a lot of you that don't understand that theory. Chapter 5. Okay. Let's go back up to chapter 3. So how to find inverse? So chapter 3, we touch on let's go back. We'll go back one step first. So we talk about determinant. So what we really want to do in this topic is actually finding inverse. Okay, determinant is just one thing you need to find before you find inverse. Okay, so determinant. What can you do? You can do cofactor expansion along any rows or column. Okay, and then this any row and column actually based on how you compute determinant for 2x2 case. Okay, so make sure based on determinant of 2x2 matrix. So make sure you know how to compute determinant of 2x2 matrix. Everything starts from there, building up from 2x2. Okay. So one important property you need to know in this is determinant of AB is equal to determinant of A times determinant of B. Okay. And then there's some invertibility regarding determinant not equal to 0. Okay. If it is invertible, it is the determinant is not equal to 0. And other property you can see, not hard to learn, but you can see. So the main thing is the Cramer's rule. Last thing, Cramer's rule. Okay. So Cramer's rule at first is used to solve AX equal to B. But you can set your B as a identity matrix, the column in the identity matrix. So you can use it to find angles. Okay, using the, what do you call that? We call it adjoint of A. Okay, 1 over determinant of adjoint of A. Okay, yeah, determinant. Okay, so if you think that chapter 5 very hard, try again. I will run through again chapter 5. So chapter 5. Chapter 5. Okay, chapter 5. Okay. Chapter 5. Please give chapter 5 another chance. Another chance. Okay. Please listen now. What is chapter 5? So chapter 5 is talking about eigenvalues or eigenvectors. So what is eigenvalue and eigenvectors? So it's just some vector that satisfies ax equals to lambda x, where x cannot be 0. Okay, if x is 0, lambda can be everything. So we don't want this kind of ambiguity there. So this is equivalent to a minus I lambda times I times x equals 0. Okay, where I just move a lambda x to the right hand side. Okay, so this is why we always talk about this equivalence here. So the null space here, null space of a minus lambda I is what we call the eigenspace. Okay. So one important thing to note here is eigenvectors with distinct eigenvalues are linearly independent. So this is the one I put inside the quiz. Eigenvectors with distinct eigenvalues are linearly independent. Right? This fact very important for us to do diagonalization. Okay, so by the diagonalization theorem,
theorem. We have A equals to PD P inverse, okay, where P has column of eigenvectors, and D diagonal entries of eigenvalues. So when we can we do this? Only when the algebraic multiplicity of eigenvalue is equal to its geometric multiplicity. Even right, okay, another thing I want to teach you. So even you don't know what these two means, right? You also can memorize this sentence. Not memorize, I mean remember this sentence. After you remember this sentence, you can go back and find what is algebraic multiplicity, what is geometric multiplicity. For me, like for example, when I was last time, right? When I see this, if I don't understand these two, I won't accept this sentence. So that means this sentence won't appear in my mind. Okay. Now I want to tell you is try to make this sentence appear in your mind, even though you don't know what these two mean. Actually, you don't realize this is how you learn when you are a kid, when you are a baby. Seriously. Actually, what you learn, you don't know what you are learning, but you just learn. That time you just accept. But when you grew up, right, you try to, how to say, you try to, I forget the English word. Yeah, you try to doubt what people say, and then you start to not believe in what people say. I'm not telling you believe what I say, but first take it in first, and then you check. Okay, so now you are grow up, you don't believe that it is true, but you believe there is something like this first. Okay, and then you doubt it. Instead of you doubt it and then I don't want to accept. That's wrong. Okay, so this is the difference. Yeah. Okay, don't say more first. Okay, yeah. So now you already grow up, you can doubt, but accept first and then doubt. Okay. Yeah. Okay. So where we stop here? Oops. Okay. So in this case here, actually we say A and D are similar, right? We talk about similarity. So here, okay, wait, let me finish here, then I make a remark. So they are similar, they are equal up to P. Okay, we call this conjugate by P. So conjugate by P, they are not equal on the nodes. A doesn't equal to D, but they are conjugate. So we say similar. Similar, 很像 similar. Okay. 相似. Okay. So A and D are similar, but similarity doesn't restrict to diagonal only. Okay. So let me make a remark here. So the definition of similarity. Okay. So let me write this. In general, similar matrices, two similar matrices might not be a diagonal matrix. Okay. So you may have D which is not diagonal, but you still can find P inverse, such that the equation. So this part important, you should review on this part, similarity. Okay. So so here I want to bring in this concept again. I hope you don't understand, but you will remember. Okay. So actually, A equals to PD P inverse means if you change the basis to eigenbasis, eigenvector basis, then A acts like a diagonal matrix. Okay, please accept this sentence. Okay, and then go and find why. Please accept this sentence. If you graduate from this course, you should forever remember this. If A is diagonalizable, that means if you change the basis to eigenvector basis, then A act like a diagonal matrix. Okay. Please remember this line. Okay. So the next part is, can you do this in general vector space? Okay, general vector space, finite dimensional. Okay, finite dimensional. We don't want to deal with infinite matrix, finite dimension. Can we diagonalize a linear transformation on the finite dimensional vectors? Okay, so the answer is yes. Okay, how to go from finite dimensional vector space to Rn? Okay, how to make this link? Okay, how to make this link? This link is the question that you always ask me. What's how to find the matrix for T relative to B? This kind of question. Okay, so I give you a linear transformation. Give me a matrix. Okay. So this is how you make. So let me draw this. The diagram you don't like, but I still want to draw it. So let's say you got a T, okay, between different dimension. One is dimension n, one is dimension m. Okay, so you got a set of bases B, and then you got a set of bases C. Okay, so there are n of them, m of them. So how you go through this, pass this to Rn? So you are taking the coordinate basis. So you are taking the coordinate basis. So this is how we make the link between isomorphism of finite dimensional subspace and Rn. Okay. If you don't understand what I say, you should take my word. Okay. Only now here. Okay. Now here you find the matrix A. Okay. So this is a general way how you find A. Just now I already tell you how to find A, right? Still remember or not? Just few slides ago. You add uh, uh you add A on TE1, sorry, TB1, TB2, TB3. Still remember? TBN. Okay, just few slides ago. This one is to train whether you can know what I'm saying or not. But you will see that this TB1, right, live in W. It's not a vector. Okay? How you take vector? Yeah. Okay. So take this one. Take this one. Sorry. Take this one. Okay. Take this one. So you take the coordinate vector of C. So you lie in the final space. If you don't know what I'm talking about, you go and check your textbook. You will see that this formula will match up. I'm telling you why the textbook is true. Okay? If you take the coordinate vector, then this is exactly what in the text. So you got this A. So this A come out to be not diagonal, something very bizarre. Okay, we don't like. Okay, we don't like. So what we can do? We can only do on square matrix. Okay, so that means we can only, let's say we fix it, change the condition here to V to V itself. Okay, let has the same setup, but just considering V to V itself. So we make our W to V now. So we change it to V. So change this to V, change it to V, change it to V, change. So make them the same. So let's say we just consider the same vector space. So if you are going from Rn to Rn, the size of A is n by n is square. Okay, so this is a square matrix. Okay, so we don't like random stuff. So what we do, we can do the next step, diagonalize it, change my D to call what? What do you want to call? D, call it D. Okay, so change B to D, where D are eigenvectors. Okay, so if we change it to D, then we can get a matrix D again. So one is a script D, one is a capital D. Okay, so this is a diagonal matrix. Diagonal matrix. Okay, so you transform your matrix again to coordinate on D, coordinate on D. Then you can go all the way from linear transformation to some diagonal matrix. Why? Diagonal matrix is easier to compute. Diagonal matrix acts like a number on separate part. Okay. So actually, what are these lines here? Okay, what are these lines? These are actually the change of basis element. Okay, so I should write dx to b, and then this is from b to. So when you are taking coordinate vector, actually you are acting by a matrix. Okay, so you see, we put all things patched up together. Okay, maybe you don't know why it patched up together, but you can see a lot of things coming in now. Change of basis, diagonalization, linear transformation, basis, dimension. Okay, everything put in together. This is the whole picture you need to see after we go through this 5 chapter here. Okay. 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 So when you do revision, right, keep this big picture behind your mind, and then I think you will read better, hopefully. Okay, keep this big picture in your mind, and then go and do your revision. So let me briefly talk about the diagonalization, and then we will end. Orthogonality. So topic 6, orthogonality. So orthogonality. So seems like we doesn't really like eigenvector basis that much. Okay, we found another basis that is more useful, which is orthogonal basis. Okay, so we learn orthogonality. What's the orthogonal vectors? Okay, and we learn what? Where's chapter 6? Okay, we learn inner product. Okay, we learn inner product. We learn inner product. Okay, inner product. U dot v equals to UTV, and then we learn how to take length using the inner product. Okay, and then we learn how to take distance. You just compute the length of U minus V. Okay, and then we compute that UV is equal to the length of U times the length of V cos theta. Okay. Notice that this is the inner product on Rn only. Okay, so we can take degree. So U dot V equals 0 if and only if. Okay, not if and only if. When theta equals to 90 degrees. Okay, I want to put if and only if, but this one is up to some, because you know cosine is periodic, so up to some shift. So this is what we call the orthogonal. Okay, so if you put 90 degree, cos 90 is 0, so this part is 0. Okay, one key what? Key logic point here is non-zero orthogonal vectors are linearly independent. Okay, this one is the one I put inside the quiz as well. So non-zero orthogonal vectors are linearly independent. Okay, so after this, whenever we see linearly independent span, we want to make it a basis. Because basis theorem said if I add enough linearly independent, it becomes a basis. So after become a basis, what to do? So we can get orthogonal basis. U1 up to UN. Remember what I talked about the advantage of this basis here? Is you don't need to go through the Cramer's rule, you don't need to go through a row reduction. You can express your y, you can find your coefficient by just taking the inner product of y with the ui divided by their length. Okay, let me write a compact notation here. So I don't want to put add again, so I just put u dot ui over ui dot ui. Okay, so you sum from I equals to 1 to I equals to n. The thing inside our note. This is the same notation. So to save time, I write this. This one is the shorthand notation. Okay, then what you do is next. You see this length keep popping up. Why not we get rid of this length? Meaning not 0 I mean make it 1. Okay, so if we make the length 1, so we just know this means we are normalize the vector u1. Okay, so we make the normalization on u1 to get orthonormal, basis or orthogonal basis, yeah, orthogonal basis. So get orthonormal set. Okay, then easily this formula here, you don't need to talk about the denominator anymore. Okay, you don't need to worry about the denominator anymore because it's just 1 now. And then there's an easy form for this, which is UUTY. Okay, go and check the note. Okay, UUTY. Okay, so the next step is orthogonal projection. Okay, so let's say if your y is not in the subspace, okay, in W, where W is a subspace with orthogonal basis. Okay, this is the special part. If you have a subspace with orthogonal basis, okay, so of course note that this y right and W right, they should live in the same vector space. So y is in V, W is a subspace of V. Okay, so only then you can talk about two things together. You cannot take something from other vector space and then compare with something in other vector space. So they should live on the same vector space, but you got a subspace. So if it's not in the subspace, then you can orthogonally project. And then it is unique in the textbook, you should see. So let me write down. So by orthogonal decomposition theorem, we can project y into W plus another thing. Okay, because if you project, there's something left over. What's that thing left over? That thing is something that is orthogonal to the subspace. Orthogonal to the subspace. In particular, orthogonal to one of the vector, which is the projection itself. Okay, so what is projection? So this projection is because this projection already lie inside the space, right? Okay, so just now we can decompose y into this the inner product with vi. Okay. So how to get v? I'm not implying that you can get v anywhere. This equation tells you how to get v. You know y, you know projection of y, so you take the difference to get v. And that is equal to y minus. Okay, you don't get it anywhere, but you take it like this. Okay, let me see. Sorry, I still got one page. One page finished, then we will continue with quiz pretty quick. Okay. So please fill up your mind. Just continue for 5 more minutes. Then we will go into quiz. Okay. So what does this do? So every vector we can project to some subspace and then find orthogonality and then project, find orthogonal vector, project, find orthogonal vector, project, find orthogonal vector. So this is what leads us to the Grant-Smith process. Smith process. Okay, so this leads to a Grant-Smith process to produce orthogonal basis. Okay, so if I don't write the formula down, try to imagine, let's say I give you 3 vectors here. Okay, 3 vectors here. So what you do in the first stage is you orthogonal project one of them, okay, and then try to find a orthogonal one. So you make your vector into this one, and this one. Okay, these two are orthogonal. Then you project the third vector down to the subspace, and then you find the orthogonal. So you go from this picture here to this picture, this picture, sorry, this picture, and why is it look weird? Like this. How to combine these two? Okay, I think. Why look weird? How? Okay. Anyway, I put 90° here. Okay. Okay. So you make your 3 non-orthogonal one into orthogonal vector. Okay. Okay. So this is the Grant-Smith process. So in practical, the projection, okay, the orthogonal projection, in practical I mean in applied sense. So maybe some of your word, you need this. You say that, hey, I cannot solve for this AS equal to B. So how? I still want to solve it. Right? I still want to solve it. So you want to solve it, so you find the orthogonal projection first. So the orthogonal projection provide a least square solution. Okay, we call it the x hat. Don't confuse with the unit vector. It's a different thing. In consistent system, AX equals to B, where how you find AX? How you find X hat? Where you solve AX hat equal to projection of column of A. Because now B project to column A, then you can find the solution because it's in column A already. so that B is in the column space of A. Okay. So that B is in the column space. So projection of B is in the column space. It's in the span of the column space of A. And surprisingly, we end in this. So surprisingly, this is equivalent to solve ATA x hat equals to ATB. If you don't want to do the projection, you can use this. Apply AT on both sides and then solve the rho reduce the momentum matrix. Okay, so this is about orthogonality. So chapter 7 is this singular value decomposition, where you can decompose n by n matrix into two orthogonal matrix and one nearly diagonal matrix made out of singular value. Okay. And about the quadratic form, right? I'm not sure it's in the exam or not because we changed it last minute. So I didn't know whether it has or not. So you can have a look. One thing that I don't really do in the class, but I did say, is the principal access theorem. Okay, the thing you can try and read in the textbook because it's nothing, just change of variable using diagonalization. Okay. Just that I don't bring you step by step to do it, but the principle is what we have learned: diagonalization and change of variable. Okay, try and read. I will provide solution to the previous year lecture now, and then you also can read on that part. But singular value theorem very important. Okay, having saying that, maybe I don't give back first. I just discuss and then later ask all of you to come here and get it, and then take a picture before you leave. So let me just continue discuss quiz. Okay. Yesterday we have a quiz 4. Okay, first question asks you to find eigenvalues and the eigenspace. Okay, eigenvalue and eigenspace. So most of you do this right. Some of you give up when you compute this. So please don't give up. Don't give up. Okay, don't give up. So you can give up in this quiz, but don't give up on your life. Okay. So don't give up. Don't give up on this determinant. And then eigenvalue, eigenvectors. If you know what is going on, you know what is going on. But if you don't know, actually we are computing the solution to a minus 7i augmented by 0. Okay, and then you get the parametric solution vector form. Okay, I don't penalize you in this quiz, but maybe I will in the test. So here say eigenspace is a subspace. It's not a vector. Okay. If you just give me this vector here, okay, you need to give me a span. I want a subspace. Okay, span of that vector. If I say eigenvector, okay, give me a vector. Okay. Okay. Some of you put S1 times this guy, still acceptable because S1 is a scalar. So scalar times that vector is a space. Right? Okay. CV, span of one vector is exactly a scalar times a vector. Okay. So some of you calculate it wrong, maybe you careless, never mind, that's fine. That's normal, everyone did it. Okay. So that's all for this question. Any question on this? So you see, my question here. You see my question here. I put some subject topic here. Actually, I'm hinting you there's something happening. Okay, later we will come to that part. So I said there's a scaling coming in. Okay, there's no scaling in this question, but later we'll see. So question 2. Okay, question 2 saying determine the flow set is an orthogonal set and perform normalization if it is into a autonomous set. Okay, so most of you know how to do orthogonal, so you just dot them together, check whether it's 0 or not. But I'm not sure why you guys didn't read this part or you don't understand this part. You don't do the normalization. Okay. So normalization, what do? You count the length first, and then you divide the vector by the length. Right? Right? Okay. So any vector divide by its length. Okay. If you compute this is 1. So any vector divided by its length, the length of that is 1. It's always 1. And then you take the length and then divide by that. Okay. Also, I hint it for the subject already. Trim your hair. Can you cut your hair like one hole like that? It's like straight, right? Okay. So perform normalization to make it into an autonomous set. Okay. Any question on question 2? Oh, good. Okay, some of you also did careless mistake when calculating this, but anyway, it's fine. Yeah, so this part here. So I say that if you consider a linear transformation from R3 to R3, I say to itself, determine whether A is diagonalizable by writing A as PD P inverse. So find me the P and D to show that it is diagonalizable. Okay. So some of you didn't realize that this is the question coming from question 1. So you go all the way, get the eigenvector again. See how many marks I gave? Only 3 marks. How can a 3 marks contain so many calculations? Huh? Yeah, so even you like don't just see, so just see the rabbit and then shoot it. Who knows the rabbit is a bomb? You know, don't just see the question and then go and then dip your head down. Okay, so make sure you read what is going on first. Okay, so yeah, but also quite a lot of you realize that this is from question 1, but I don't know why some of you don't refer to question 1. You use something from question 1, but you didn't refer. So make sure next time when you want to refer, you say refer to question 1, or by question 1, we got this, we got eigenvectors. Okay, make sure you refer back. So make this into the diagonal matrix. So this is where I hint in this subject topic here. Okay, that scaling. So we make scaling on different basis vector. Okay, make it a diagonal. So if you know it, you know it, but still have some of you don't know this concept here. How to diagonalize the matrix? You need to use eigenvectors. Okay? Eigenvectors. Eigenvectors. Okay, make sure you really know this. Okay, eigenvectors. So one more for P, one more for D, one more for putting the right direction. Okay, that's all. Question 4. Question 4 here. I put truth or dare here. Anyone know what is truth or dare? Yeah, 试一下啊。你说的真心话大冒险。But some, you know, someone what they put truth dare. So you don't want to answer the question, so you choose dare. Okay, so there is not no, there is something else. So I asked whether first, if V1, V2, V3 is an orthogonal set, is the set a basis? Okay, can the orthogonal set in R3 3 vector form a basis? 2, if you have 3 eigenvectors with distinct eigenvalues, can they form a basis? Okay, and then I ask why. Okay, I don't ask you to prove it, I just ask you to state why. If this is a math class, then I will ask you to prove it. So since this is not a math class, you just reason is enough. Even if you don't state the theorem, it's fine. You just know what is going on, also can. So, okay. So the first one, actually, I already keep repeating in the Tuesday and Wednesday class. Right? Orthogonal set can contain 0 vector. If an orthogonal set contains 0 vector, then the set won't be linearly independent. Right? Because you can put a non-zero scalar in front of the 0 vector, you still get 0.
But if there are eigenvectors with distinct eigenvalues, then the vectors are linearly independent. And you have three linearly independent vectors in R3. Dimension is 3. So by Bayes' theorem, they form a system. So this is the full solution. So I set this as the last question for marks because to get distinction, I think you need to know this. Yeah. So the how I set out the question is based on the level and then something I want to get out of this class. So I set it as a question. But anyway, our quiz is about average is 19.2. Actually, not too far from the first average we get from the first quiz. And then the second class, they got 17.3. Yeah, so just keep it up. Actually, quite a lot of you do quite a good job. Actually, some of you got large improvement. For example, Peng Jiarui got full marks. Liu Hanling also got full marks. And then some of you Fang Hao also. And then Xilei not here today. Not here. Yeah, Xilei not here. Hey, I haven't passed you this to sign, right? So later you come here and sign your last signature, and then take the last photo, and then you can leave. Okay. Lin Yuxian, who is Lin Yuxian? Can't always come. Oh, Lin Yuxian, yeah. Okay, good. Lin Hao, Ying Jie, Nian He, Qing Ya. Okay, good. So, any last question? Tomorrow I still have an office hour. Just feel free to pass by 8:30 to 12:30, or you have last night question. You just send me. If I sleep, then I reply tomorrow. Okay. So you just send me email, Teams. Okay. Don't give up. Wow, I haven't give up. Okay. So yeah, just find me. You still have 4, 3, 6 days, about 5, 6 days. So don't give up. So later come here, sign your last signature, and then take a photo. Don't bring it back, and then you can leave. So I will see you again. Probably won't see most of you next semester because I'm teaching AIT and math student. So if we can meet, maybe we can meet in GE again. Who knows? Okay. See you when I see you again. Bye.